Hello. Yes. In this video, I would like to show you how to use Microwind, a software tool. Microwind is a tool for designing VLSI layouts. Okay, so this is the window for Microwind, which is freeware. You have a palette here. First, what you do is you select a foundry from this, go to File, and then select foundry. So it will open a list of foundry, that means .rule files. So design rule files. Select one of them. So for example, a 70 nanometer technology, open it. So it will open the design rules of that particular technology and the masking sequence in the palette here. So let me show you how to draw an inverter in this 70 nanometer CMOS technology. A CMOS inverter will have a PMOS transistor at the top and NMOS at the bottom. Okay, so both the gates of PMOS and NMOS are connected together, and that is given to the input, and both the drains of PMOS and NMOS are connected together, and the output is taken from that. And the source of PMOS transistor is connected to VDD, source of NMOS is connected to VSS. Okay, first let us try to draw a PMOS transistor, so which will be sitting in N well. So let me draw an N well region like this. So within the N well, we have to make a P plus diffusion area. Okay, so P plus diffusion, let me draw like this here. Alright, okay. So then gate is polysilicon. This gate, this source, this may be drain, gate, and source. So what for PMOS transistor, the source will be connected to VDD, and which is sitting in the N well should also be connected to VDD. So to take contact from the N well, okay, that will come to that. So we have to take contacts from source, gate, and drain. This is the source. Okay. So take contact, open a contact window, and then put a metal, or directly you can put P plus contact diffusion on metal. So click on this, put one contact here. Click on this, put another contact here. And to take contact from poly, there is a metal poly contact. So put that here. Alright, okay. So this completes your PMOS transistor. So to make an NMOS transistor, wherever N well is not there, so the other area is a P-type background. So in that you can directly, no need to draw a P well there. So it is already background is P-type. So what you do is draw P plus diffusion. Sorry, N plus diffusion for making NMOS transistor. Okay, so it will be something. Let me draw like this. Same size as that. Okay, so again the gate will be polysilicon only. So gates, as said, both gates will be connected to each other. They will be like this. Now put contacts from the N plus source drain. Now this is a source, the other side is drain. So both drains will be connected, yeah, as I said in the beginning. So put the contacts to N plus regions like this. Alright, so this completes the contact. Now we have to connect the drains of both MOS transistors together with a metal line. So let me short these two like this. Okay. Now take an output from connect the metal line to this, to both the gates. This will be your input, and the source of PMOS has to be connected to VDD, and the N well also should be connected to VDD. So to take a contact from the N well, what you have to do is you have to open make an N plus diffusion into that and take contact. So put an N plus diffusion on N well, N plus to metal contact. Okay, so something like this. So now you connect both of them, both are top metals, and take like this. So what does it mean basically? So you are having an N well, within that you have a P plus diffusion, and this is the source of PMOS, and the substrate of PMOS is N well. Both are connected together and should be given to VDD, positive supply, and the source of NMOS has to be connected to ground. So let us connect the power supplies. So there is a VDD supply here. Now this has to be connected to VDD, and the source of NMOS has to be connected to ground, that is VSS. Okay, so this is VSS, and this will be your output, and these are input. So input, let me give a clock signal to the input like this, a clock signal, and let us see what is happening at the output. So we have to put a visible node here so that you can monitor it. Okay, so this completes the layout of an inverter. Okay, so the top one is PMOS transistor, bottom one is NMOS transistor. So this is your output, this is your input, this is your VDD supply, the bottom one is VSS. Then this completes the layout. So what we can do, you can simulate this inverter and see for its behavioral. Okay, so the transistors are represented by their models to do the simulation. So if you go to simulate, there is select model is there. So level 1, level 3, BC4. So this is basically the transistor models for the given chosen technology, that is 70 nanometer CMOS technology that we use. Let us choose a model BC4, Berkeley short channel IGFET model. So it has simulated. Okay, so let us reduce the time here. It is up to 6 nanoseconds. Let us make it up to 1 nanosecond so that we can get okay. So initially it is getting charged. Now you can see that this is input. Okay, so when input is going low, output is going high, and input is going high, output is going low. There is a a time uh, delay is coming up there. How much is the time delay, rise delay and fall delay? They are mentioned here in terms of picoseconds. Okay, so this is a timing analysis of inverter. Alright, so this is what you can do in this. Suppose if you do the same analysis with a different model, that is say level 1, you can see the timings are not different. Actually, see the time delays are not modeled properly. So level 1 is a primitive model. So BC4 is an advanced model, so which gives a precise prediction of circuit behavior while doing the simulation. So you can also do the design rule check. Yeah, here it says the extra annual surrounding diffusion is less than 6 lambda. So there is a violation here. So what does it mean is the annual over this diffusion is slightly lesser. It has to be 6 lambda. So what you do, you select it and stretch it further slightly, and then you do this design rule check again. So now there is no design violation. Design rule violation is not there. Okay. So since we have drawn arbitrarily, so there is a chance of design rule violations there. So one more thing that you can do, interesting thing is that you can see the cross-sectional diagram along a particular line. So I'm drawing a line here along which I want to see the cross-sectional diagram. Okay, so this is a PMOS transistor which is sitting in N well. So this is a green one is N well. Green one is N well. So this side is your drain of PMOS. This is a gate. Red one is a polysilicon material. Drain is connected to metal one through a hole, contact hole, and source is connected to VDD through a contact hole here, a metal layer. And as I said, we have opened N plus contact to take a contact from the N well. Okay, so this, what is this? A height one. This is a thick oxide. So this is the active area, which is called where the thick oxide is not there, and the field area is where you have a thick oxide. In the active area, no thick oxide is there. Only gate oxide, very thin oxide will be there. So this is how you can also verify. You can, for learning purpose, you can see how the cross-sectional diagrams of the devices look like, and the dimensions and heights of various layers it is given here. So like there's so many things that you can do. Yeah, this is an inverter. So in this video I've shown you how to draw an inverter in Microwind, and how to check its transfer characteristics timing diagram, and how to see the cross-sectional area. So all these things that you can do in this. So okay, see you in the next video. I'll show some other things. See ya.